it seems to me that people lose easy marks on certain questions, so I'm going to look at some energetics questions, which I think are questions which everyone should get full marks. They should be relatively straightforward. Okay, so when we did the energetics topic, we learned that we could work out the energy transferred in a chemical reaction from mcΔT. And people are all really comfortable with that, but sometimes stumble around and make mistakes on some relatively straightforward questions. And when we're doing Q equals mcΔT, let's make sure you're really clear that in this equation we're working out Q, which is the energy transferred. And that's usually energy transferred to water. In fact, in any question you'll see, in an IB question, it's the energy transferred to water. So this is not going to be a number that's a negative number. It's how much energy has been transferred to that water. So just always give it as a positive value. This is the mass of the water, and we want that in grams, okay? And C is the specific heat capacity of water, which is always given as 4.18. You can work out the units from the equation, but the units are joules per Kelvin, or per degree C if you like, per gram, but that's given to you. And delta T is the change in temperature. Now people get this equation for Q, the energy transferred, and the equation for delta H muddled up. Okay? So if it asks you about the energy transferred, work out Q. If it wants you to work out the enthalpy change for a process, enthalpy change per mole, you'll be working out delta H. Now if that's an exothermic reaction, use minus Q divided by N. Now enthalpy change per mole is given in kilojoules per mole, so we need to have converted the Q to kilojoules now, and N is the number of moles of the reactant we're interested in. Let's say it's burning of methanol, for example, or whatever it might be. It's the number of moles of the limiting reactant in the reaction you're studying. And you usually have to work that out by dividing the mass of that reactant, which might be a gram or something, divided by the formula mass. Now it's easy to slip up with questions like this. You've got two equations you remember, but which one do you use and how? And I'd encourage you to do a few past paper questions on this. I'm going to look at a couple of questions now. I'm going to start off with one, I think this is in the specimen paper, and the first question was working out a balanced equation, which I'm not going to do. And the second question was to calculate the maximum energy produced when 2 grams of C17H36 is combusted. So this is looking at the question a slightly different way around to what we'd normally do. The equations we know are, or in this case we've been given enthalpy change for combustion, so we're going to be using that in an equation. So the equation is delta H equals minus Q over N. It's an exothermic reaction, and so to work out Q, just rearrange that equation, or put the numbers in and rearrange. So delta H equals minus 11,350 kilojoules per mole, huge amount of energy, and I've worked out the number of moles by doing the mass of the fuel, which is 2 grams. And notice I've written it down not as 2 but 2.00 to match the exam paper, and I worked out the formula mass of C17H36 as 240. Lots of people, when we did this in class, gave it to 1 sig fig there. Please give the value to at least 3 sig figs, given that the input data is to 3 sig figs. So rearrange that equation. So Q is equal to 11,350 times that number, and you end up in kilojoules of 94.6, or joules as 94,600. Again, 3 sig figs there is appropriate, but please give the units, make it clear whether you're giving the answer in joules or kilojoules, whichever is fine, as long as you're clear which one you're doing. The next part of the question, people really struggled with, even though it's a relatively straightforward question, I would argue. So the maximum temperature change when 500 centimeters cubed of water, which by the way is the same as 500 grams. We can assume the density of water is 1 gram per centimeter cubed. So we're therefore going to use Q equals mc delta T. We know Q, we've just worked it out, we'll give that in joules now, 94,600. The mass is 500 grams. 4.18 is the specific heat capacity of the water, and then delta T like that. I don't even feel like doing the sum because you can rearrange that equation dead easily. Delta T equals 94,600 divided by those two numbers. Done. All right. Just to finish off, very common question. Assumptions made in this calculation is one really important one is there's no heat loss to surroundings. Another one might be, because this is an enthalpy change of combustion, so we're assuming that it's complete combustion. And there's a number of other possibilities, like we're going to assume the water that we're heating is pure, and therefore the specific heat capacity and density of that water are what we've suggested there. But this question was done horribly. So why do biofuels, this is done horribly by both years that have done this paper, why do biofuels contribute less to climate change than fossil fuels? Well, the biofuels are just fuels that are made from biomass, and often they're molecules that have long chains of carbons. So it might be something like biodiesel. Have a look at the structure of biodiesel if you want to. Now, the key thing about biofuels is that, or it could even be wood. The thing about biofuels is that they're fuels that have been generated through growing of plants, and when plants grow or trees grow, they photosynthesize. So CO2 is taken in from the atmosphere during photosynthesis is equal to, or should be equal to, all things being ideal, equal CO2 that's released when you burn them. So you do produce carbon dioxide, but it's taken in again when the plants are growing, and so we call that the idea of carbon neutral. Okay, so they don't overall produce any carbon. And we're not going to do the last question now.